Welcome back, Algebra Express. We are in section 5.3. This section, we are going to start talking about exponential functions. And so this is titled Exponential Functions and Models. If you look at the exponential function, they just kind of throw it out at you. But basically, we have a function, so f of x. If you want, you can rewrite this maybe. It's going to be a y quantity, like y equals. And so if we're looking at our x quantity, you might notice our x quantity is in the exponent. So when we talk about an exponential function, what that means is that we're going to have variables up in the exponents. So c is the coefficient. Base. Variable is the exponent. And so you should probably have an example. You could plug in numbers for e to the x. So this might be like an example of an exponential function. They don't tell you what c is or what your a is, but I want to think about it for a minute. And so for the function x equals to the x, equals c to the x. And if we think about the point at x equals 0, what is x equals 0? That's another way to talk about my y-intercept. So if I want to talk about my y-intercept, plug in. We're talking about 0 exponents. So what I'm actually getting out of here is just the c. So if I want to know what my y-intercept is, it is the c. The c and the y-intercept, the coefficient, are the same thing in our exponential function. There is one other thing there that we got to talk about. There is a c and there is an a. There is a coefficient and there is a base. So what is this base doing? If we think about our exponent and our exponent going up, every time we add an exponent, it's like we're multiplying by another a. So a is going to be the rate of change. Okay. So sometimes when they throw out exponential, they like to kind of compare it and contrast it to linear functions. So if you try to do this with a linear function, we're going up one each time in the x. You'd be trying to find the slope here. You might say this is like +5, but then we go +10, +20, +40. We don't want to think about these like a linear function. So if we can't add a constant amount, it is not linear. But you might notice a pattern in the numbers that you were adding. What we're doing is 5 and 5, 10 and 10, 20 and 20. To get to the next one, what we're doing is we're doing this thing twice. If I go from here, what I'm doing is I'm doing this twice, or I'm multiplying this thing by 2. X is going up 1. And for each one that you go up in your x, you're multiplying by 2. So kind of similarly to the way that we did slopes with linear functions, but instead of adding, now we want to think about these things being multiplied. So if you can add a constant amount, it's linear. If you can multiply by a constant amount, then it is exponential. And now they want us to find C and A. My C, I talked about that just a second ago. That is my y-intercept. If I'm looking at my y-intercept here, it's a value of 10. Talked a little bit about A. It is the rate that it changes. That is the 2 that we're talking about multiplying by. So A is going to be the amount that you multiply each time. C will be like your y-intercept. And I wanted to... We're like right there. And if you want to plug in some numbers and check it, we plug in 0, we should get 10. We plug in 1, we're multiplying by 2 once, we should get 20. We plug in 2, we get 2 squared. 4 times 10 will give us 40, and so on. So if you want to sort of eyeball this thing and plug in some numbers and check them, they should come out. All right, that is the first example. So C is like our y-intercept, A is like the rate of change. And so we look, we notice these are one by one. They're nice and they give it going up one by one. What am I doing with it? So going from 45 to 15. And this one we definitely went up. This one is not going up. You might notice that. So it's like we're dividing by what? And the number I'm thinking is like we're dividing by 3. But we don't want to think about it as division. We want to think about it as multiplication. It's like dividing by 3 is multiplying and flipping it, right? So dividing by 3 is like multiplying by 1. Divide 15 by 3, we get 5. All right, so I got to fill out my information, my C and my A. I want to know the coefficient, which is like my y-intercept, which is like this value 5 right here. My A is the 1. So I am looking at this thing, and I want to go ahead and write out my function because I'm right there. I got my C and my A. I might as well. And I have other to the x. Okay, next thing. I'm looking along here. We have a table, we have a graph, so they've been giving us it numerically. Now we want to go from graphically to symbolically. And so I want to find my C. So my C is like my y-intercept. That should be hopefully pretty quick. Here's the value of 2. Now we want to talk about A. So I'm going to have to find 2 points probably on here. Going from 4 to 2. The point minus 1, the point. That point is also going through. If you wanted to do this symbolically, you could do this symbolically. You might be able to tell from these numbers what is happening. But a key way to get at it, we can fill out information. We know our C is 2. So f of x equals 2 times a to the x. We could fill out one of these things. And I believe you're going to want to fill out one that's not the one you already used, right? We already used the 0, 2 to get to our C. So probably not that one. And if I'm thinking about it, I probably don't want to plug in negatives. 1, 1 looks like a really nice sort of thing to plug in. to my x. I can solve my a real quick by dividing by 2. It would be 1/2. If we look at 4 to 2 to 1, these are going down by a factor of 1/2 each time. 1/2. If I want to finish up my function, throw a little paper up here. We're running out of here. F of x. I know my c is a value of 2. I know my a is a value of 1/2 to the x. And so if I want to finish off writing the function, it should look something like that. Okay. Next problem, page 2. Ooh, now we get to compound interest. So we start with $1,000, and it says something about investing at 5% compounded annually. And so here they're giving us the number of years. And so the first thing I want to do is think about $5 of 1,000. 0.05 times 1,000 if you want. But if we're doing 5% of 1,000, it's 50. Okay. So what is happening if we're investing at something that is 5% compounded annually? What compounding means is we're going to figure out the interest earned on that thing. So we're going to calculate and crunch the number and figure out how much money you've earned. And we're going to do this every year. We're going to add 5% to this thing. So if we start with this, the first year, we're going to add 5%. We're going to get $10.50. And now this is where compounded interest differs from simple interest. If I was doing simple interest of 5%, I would just add 50 each time. Now, compounded interest takes interest on interest. So simple interest is just a flat amount that we would add, but now we're doing compounding interest. If I want compounding interest, I want to know what 5% of this is. And if I do 5% of 10.50, which is the same thing, I should be getting the amount of 52. So I'm going to earn a little bit more in my interest, like $2.50 more this go round because I earned $50 last time. So I'm taking interest on the $50 interest. What I'm doing, I'm taking my $10.50, adding it to my $52.50 to get to my next year. So $10.50 plus $52.50 is going to give me $1102.50. Let's put my 0 there. There we go. All right, so I want to think about what we did. We did 5% of 1,000, which gives me 50. So I took my 1,000 and I added 5% of 1,000 with 52. Okay. So this is going to give me 10.50 when I add these things together. What I want to look at is this step right here. I have one of the thousands and I'm adding 5% to it. So there is another way I can sort of think about this. This is like 1 plus 0.05. And I have 1,000 in common that I can factor out from this thing. So this is sort of like I'm doing 1,000 and 1 plus 0.05 gives me 1.05. This is sort of like I'm doing 105% of the 1,000. So if you're doing 5% interest on 1,000, the next year you're going to get 1.05 or 105%. If we look here, what I'm actually doing here to get to the next step is multiplying this thing by 1 plus my interest. So I take one of the $1,000 and I add 5% of the $1,000 to it. It's like doing 105% of the $1,000. 1.05 times 1050, that's a quicker way to get 1102.50. And we learned it, so use it. Don't lose it. I don't know. The 1.05, if we know that this is a probably there. Fill out that last number. So we do 1.05 times 1102.5. It's going to give me something I have to round. It is 1157.60. if I round it. If you round this up, that is fine. Although, being honest, if it's 62.5 and it's a bank, they're probably going to round it down for you. They probably get that extra benefit of rounding. Okay. What does my investment in T years look like? Okay, so you might notice the exponential function that we had on the previous page. So we need to fill out the things that are not our x and y variables, or the c and the a. So we want to fill out c. What is my c? My c is my y-intercept. That is $1,000. Or the principal that I started out here. The a is the amount that is changing. 1.05. And this is to the x. What is the investment in T years? So maybe they want some different symbols. I don't know. Maybe I'll go ahead. This would stand for the accumulated amount. 1.05. Some variables to suit the problem, sort of. Where T is time. They want year T. Okay. Instead of X, we'll swap it with the T. Okay, and then they get the little symbols for powers on a calculator. So if we want to do exponents on a calculator, there's either the little caret symbol, or they will have like a y to the x sort of thing happening. So I think most of the graphing calculators go with the caret symbol. Okay, so we have a compound interest formula. Okay, in this previous problem, we basically did this, but our n was 1. So n is the number of compounding periods. So in my other class, I actually introduced this one first. And if we look at this, this is exactly what we did with this problem. We have our accumulated amount. P, our principal is $1,000. 1 plus R, which is the interest rate of 0.05, is going to give me 1.05. And then my T is the variable that stays there for this time. So if we compound it once per year, let n be 1, we get a little bit of a simpler formula maybe that you could use. It is basically the same formula as n being 1. If n is not 1, there are two sort of things we have to do. one thing is the rate changes. So our interest rate is going to change. If we do it 4 times per year or quarterly, N would be 4. We would have to divide our interest rate by 4 to get the quarterly interest rate. And then NT, N times T is going to represent the number of total compounding periods. So like if I compound it 4 times per year for 8 years, figure out I've compounded it a total of 32 times. So this exponent has to represent the number of times we're crunching this thing or compounding it. All right, so interest compounded N times per year, A equals P times 1 plus R over N to the NT. That's where they're getting this formula at. They just kind of throw it at you. I thought I'd give you a little bit of background on where it's coming from and why they're doing certain things. So it is the thing that we found out previously, but we have to change our interest rate and we have to reflect this thing to represent the total number of compounding periods. Okay, so the principal is an amount that you start with. That is like the $1,000 in the previous problem. A is the amount after 2 years. Sometimes they like to call this the accumulated amount. R is your annual interest rate, and they're going to give it to you in a percentage. We're going to have to convert it to a decimal. N is the number of compounding periods per year. So like I said, compounding is when you crunch the number, you figure it out. And the amount that you get is going to actually change with the number of compounding periods. So ideally, the more you compound something, the more you should get out of it. A principal of $1,500 is invested at an interest rate of 6.5% compounded quarterly. How much is present after 5 years? Ooh, they are giving us a lot of information. But I want to look. This is my principal. So that should be my P variable. This is my R. It's giving it to me in a percentage. I want to convert it to a 0.065. Next thing they say, it's giving me the number of compounding periods per year. And then they say after 5 years, so this is giving me the number of years, which is T. 5. So I think a lot of things that, or one of the things that people mess up is that they see these things like it's compounded quarterly and after 5 years. You might want to like take note in your brain somehow. Like we do have 2 variables that are sort of time related, right? This gives you the number of compounding per years, and then T is the number of years. So they are both measuring a sort of time sort of thing. But one is the number per year and one is the number of years. Okay. But that said, I think we have enough to just like plug it into the variables. The number is where the variable should be. 100 is my P. I have 1 plus R over N. 0.65 over my N. I'm doing this to N times T, which is 4 times 5. All right, so order of operations might have to come in here a little bit. But we get something like 1,500 outside of parentheses. Hopefully you realize what we're going to have to do is parentheses. So the first thing I'm doing is doing 0.065, and I'm dividing that by 4. So this is giving me 0.01625. Ooh, drop that. And if I go back and look at this, let's see if I can fix this a little bit. If I want to look at this equation, I want to do this first, and then I'm going to add these two things. If you want to know how to do this, I'm going to have to multiply these exponents before I actually take the exponents. So if I'm seeing this multiplication up here, it's kind of sort of like I have maybe parentheses in my exponents. I have to crunch that exponent before I actually use it as an exponent. Okay, so I'm looking at this thing. What I want to do, I'm going to add these together real quick. Those are going to be really easy to add together. I'm just adding a 1 on top of a decimal. So those should hopefully be pretty quick. And now, in order to do this, this is the thing that you're going to need your calculator for. I'm going 1.01625, and I'm raising this to the 20th power. That is giving me somewhere around 1.38042. Let's see, if I don't round that, I get 207063. If I do round it, I'm getting something like 1.38. Let's see how close it is. 207063 on the dot. So if I round it to this amount, it gives me exactly what I would have gotten. I didn't round it, and then just round it up. So that gets you pretty close. 5 decimal places. Okay. So now they want to talk about this thing with A base E. And so what they're doing is they're trying to simplify this a little bit. What they're allowing R to be is rate of 1. And they let T be equal to 1. They want to know what's happening with this N. What happens if we let N be really, really large? And what happens with this 1 plus 1 over N to the N? As we let it be really large, you might notice we're increasing by like what, 9 here. We're going to get like 2.59. We're getting 7 point. You might notice it's moving less and less. And these are getting drastically more and more, right? We're multiplying by like power 10. So there are 9 between this one and this one. There's 99 between that one and that one. There's 999 between the next one, right? Something like that. There are a lot between those things. Did I do that right? No, there's 9 and 900. Sorry, I don't know how to subtract anymore. 9 and 900. There's 990, 900, right? Is how this thing is going up each time. And despite increasing this and increasing this drastically more, this thing is kind of sort of leveling out. So what's happening? Look at my little graph. What a picture I have in my head. This is my N getting large. I'm getting larger and larger. And close to this number. Horizontal asymptote thing happening, right? It's reaching its sort of limit here. And what this limit actually is, if you go to your calculator and you type the lowercase e to the first, you will get that number or something pretty close to it. So second e to the first gives me 2.71828, that number right there. 1828. And this thing, it keeps going. That is an approximation. So this is E. Is Euler. This guy's name is called Euler. It starts with an E, just like the Houston Oilers. or wherever they are now. Who cares? It's not in Houston. So it's not Texas. Who cares? So e to the first is named after this guy named Euler. He came up with a lot of crazy identities. And so we named a variable after this guy. And this, like I said, is an approximation. E is an irrational number. It's going to go on and on forever, not repeat, sort of like pi, sort of like square root of 2. If we look at these things, we want to approximate to 3 decimal places is what this thing says. So this thing is basically a calculator check. Can you find E on your calculator? So if you're using one of these, you might notice it's like the opposite of the natural log. So we are talking about exponentials in this section. Pretty soon, I believe the next section, we will be talking about logarithms. So with that said, we are almost at the end of the semester. I want to encourage you to keep going. This is exponentials, and you have to know exponentials to get to logs. We're going to define logs kind of based on what we're doing here with the exponentials. So I hope you are still staying astute. With that said, I'm going to hit E and I'm going to hit 1.8. So again, I believe we've gone over scientific notation before, but don't confuse this with the uppercase E. Like if I want to do 1.8, no, let's not do 1.8. Let's do some different numbers. Let's do like 2.4. And if I want to do the uppercase E, that would be scientific notation. Okay, yeah, it's here with the comma. So if I want to do, this would be like 2.4 times 10 to the, I don't know, 5. It's going to give me 5 decimal places. So that's scientific notation. Just to remember, remind you a little bit like how the calculator types things out. Or if I do this with a bunch of zeros, it's going to give me probably back in scientific notation. So that is something different. Uppercase and lowercase e are different things. Use the lowercase e. That is opposite of your log. Use the uppercase e. I don't know what your calculator is going to give you. Probably give you an error. Syntax error. Yep. Okay. Oh man, I typed this in my calculator and I didn't even grab it. So e to the 1.8. Let's do this again. 6 points. And I want to do 6.9. We round it up. So we're rounding up a 49 to a 50. There's my 3 decimal places. Okay, so what does this mean about our formula? They kind of skim over that a little bit. But if we look at this thing, and we let n be really, really large. So what we're saying is that we're letting n sort of go to infinity. So we're compounding this, and when we compound it, we talk about actually crunching the number to figure out the amount of interest that we're earning on this thing. So how many times can we figure out the interest on this thing is the next question. Well, we can keep compounding it. We can keep compounding it more and more. We can keep compounding it. And now's the crazy thing that we can only kind of talk about in math. We can compound this thing infinitesimally many times. What the heck does that mean? That's a good question. It is like one of those things that it works on the paper, right? We can keep doing this. We can do it infinitesimally many times. We can keep dividing the number of compounding periods. So we can compound it every month. We can compound it every day. We can compound it every hour, every minute, every second. We can keep dividing the time, right? The amount of compounding periods increases. We keep dividing the amount of time that we're compounding it in. So if we compound it infinitesimally many times every second, what ends up happening is our formula is approaching this E sort of thing. So this 1 over 2 accounts for this much of your formula. We get the 1 over that, and we let T and our R be 1. If our R and our T are not 1, we have to account for that. So what ends up happening is basically this thing right here is approaching E, and it's going to approach E to the R is what's going to happen. And we're going to have E to the R to the T. So this is going to approach E to the R to the T. And what ends up happening is we get this next formula. So if we want our accumulated amount, and what we call it being compounded infinitesimally many times, is we call it continuously compounding. So if you see the word continuous, think about the PERT formula. There is a shampoo called PERT. So if you want it to be continuously, think about your PERT formula. A equals P E to the RT. And all these variables were defined before. P is still our principal, R is still our interest rate, and T is the time in years. What you might notice is that N disappears with the number of compounding periods because we are compounding it right there continuously. So we have a completely different formula for this. There is no N. N is an infinity. How much money do you need to invest now at an interest rate of 10.25% compounded continuously to have 100,000 in your account after 18 years? Round to the nearest cent. Okay. Okay. That's kind of a weird problem to give y'all, I think, but they did it. So this one is a little different than the ones that we did previously. Interest rate is 0.25 or 10.25%. It is compounded continuously. So the second you see this, I want you to think in your head A equals PERT to the RT. You want to have 100,000 in your account after 18 years. And what they want us to solve for is how much I would have to have initially. How much do you need to invest now? So the initial amount principal. So this one we're going to have to do a little bit of back solving to figure out what our P is. But it is 100,000 in my P number. That is just a constant number there. Sort of like putting pi there or something like that. So E to the R, which is my okay. So this is 100,000 equals P E to the, okay, so we got to do a little bit of PEMDAS maybe on this. I got to multiply my exponents of 0.1025 times 18. If I multiply those two things together, we get P is E to the 1.8 for 100,000 equals this. So I want to solve, and this might look a little funky because I just threw the E at you, but E is just a number. I want to solve for this. This is being multiplied. So if I want to get rid of something that's being multiplied, what I got to do is I got to divide. So I'm going to take this 100,000 by E to the 1.8. I've just got to figure out what this the number over here is. So I'm looking at this thing, and now it's calculator time, basically. I do 100,000, and I divide by e to the 1.845. Or if you want to do e to the 1.845, and you can do 100,000 divided by that. 1, 2, 3, divided by. What 1.845 should give you somewhere around 6.328. So this is just a number. This is rounded, so it's not exact. It is going to be approximate. So if I do 100, so let's see what the approximate is. Let's see how close. 328. And so if you do this, you will be just a couple cents off. Round it to 6.328. I'm going to get something like 158.02.78. 158.02.78. And so that is rounded. If you didn't round it, when I do things in my calculator, I just recall the answer and don't usually round things. You're going to end up with 158.02.53, right? So here's the thing. If you're showing your work correctly and you wind up like maybe $1, a couple dollars, or a couple cents off because you rounded it to like 3 or 4 decimal places, that's fine. Like if we're investing, what, $15,000, almost $16,000, do you think you're going to care too much about like what, 25 cents is the difference there? Probably not too much. It's kind of the take a penny, leave a penny policy, right? Take a few cents, leave a few cents. It's all right as long as it's pretty close. You're showing all your work. Just don't start rounding like things to like 6.3 or something, right? You give me a good number. Don't start rounding way up here. Like keep this 3 decimal places. As long as you're pretty close, within a few cents or within a few dollars, and you're not just rounding like 1 or 2 decimal places. If you're actually going 3 or 4 decimal places, it should be pretty good. You should be pretty close. I would say 3 to 4. They're saying 3, I think, in the notes in the previous problem. You should be pretty close. Okay, so now we want to look at these things graphically and think about what these things look like graphically. Okay, so like looking at your notes ahead of time, I think is a good strategy. So I want you to look at like what they're doing on this page. We're going 2 to the x. So this is like if our base is larger than 1 is what we're doing here. And they're going to do one that looks like a half to the x. So this is like if our base is between 0 and 1 is what we would say, right? It's a fractional amount between 0 and 1. And so I want you to think about what happens if you multiply by a number that is larger than 1. So that is what we're doing here with these exponents. And so we have done negative exponents before, but this first one, if I want to figure out f of x, my f of x, when my x is a negative 3, looks like 2 to the minus 3. This looks like 1 over 2 to the third, or 1/8. And I can fill this in for each number. F of x equals 2 to the minus 2, 1 over 2. I plug in 0, 2 to the 0 is going to give me 1. And so you might notice if my a is 2, you can go in and you can plug in number by number equals 2 to the minus 1 is going to give me 1 now. Or you can notice that each time I'm multiplying by 2. So 2 to the first is going to give me 2, 2 squared is going to give me 4, 2 to the third is going to give me 8. All right. We have our points. We have our points. We want to make our graph. We want to go -3 and the fractional amount. And if you want to do 1/8, I don't know if 0.125 might make it easier. 0.25 helps that at all, but it does. It helps you approximate. About 1/8 of the way up. When it is definitely approximating. -8, that's a -1/4, this is -1/2. 0, I'm going through 1. At 1, I'm going through 2. At 2, I'm going through 4. I'm going to go through 5, 6, 7. Oh man, I did not make it a third one right at the top of my graph. But if I'm graphing this thing, you might notice it's going up and it keeps going up. That way. It's like it's coming down. As we think about getting a larger and larger negative, our denominator is going to keep getting larger, is what's going to end up happening. And if our denominator keeps getting larger, this thing is never going to hit 0, but it is going to get really, really close to 0 from the positive direction. And so this is what our graph looks like. So this is an exponential graph. And maybe one thing to notice is that the rate from here to here is less than the rate from here to here, right? So one thing about exponentials, and one thing that really kind of trips people up, I think, is that we are really used to linear functions and having a constant rate of change. The further we go out, the steeper this thing is going to be. So this thing is just going to shoot up and up and up and up real quick. We're going to have to like start zooming in on it just to see what it's doing, sort of, right? We're going to have to change the window even to look at this thing pretty quick. With that said, there are a lot of things that kind of grow exponentially naturally, right? Populations tend to grow exponentially. Them two people have two people, and then them two people have two people. Rabbit populations, human populations, these sort of things tend to grow exponentially. Other things, viruses, tend to grow exponentially. So this is also, like some people are worried you're just going to start out really kind of small. But as the virus progresses, it's going to progress exponentially. And as it carries further and goes further up, the more it goes up, the more it's going to go up, sort of thing. But here's some defining features of this basic sort of exponential graph that we're looking at. Like I said, our base is going to be greater than 1. So if we have a fractional base between 0 and 1, it's not going to work. And we're not going to talk about negative numbers as our basis. But that is also a possibility. It will do something a little weird. Here we go with the y-intercept. If there is no c, so or if our c is 1, right? If our c is 1, our y-intercept is going to be 0, 1. It's increasing fast in the first quadrant. And the x-axis is a horizontal asymptote. So what we notice is, like I said, it's getting close to 0, but it never hits 0. So y equals 0, or the x-axis, is a horizontal asymptote. Okay. So we have this graph. Now I want to think about 1/2 to the x. Okay. So if we want to go 1/2 to the -3, -3. take care of the negative first, I think is what I'm going to do. I'm going to do 2 over 1, and I'm going to change a positive 3. You might notice this is just 2 over 1, or 2 to the third, which is 8. So this is giving me 8. If I go 1/2, to the minus 2 would be the next number I'm evaluating. You might notice this is like 2 over 1 squared, which gives me 4. And you might notice each time I'm going to half the thing. So half of 8 is 4, half of 4 is going to give me 2. Or you could do 1/2 to the minus 1. 1/2 to the minus 1, we would flip this thing and it would be 2. 1/2 to the 0 is going to be 1. 1/2 to the 1. If you're half a new square, we're going to get a quarter. If we take a half and multiply it together 3 times, we'll get 1/8. So you might want to go back, sort of look at this previous graph you drew out, compare and contrast those tables, see how they look. And what you might notice is they look very similar. This one is just sort of flipped in this direction, right? One, we get a 1.5, we get a 2 at a quarter. We get a minus 1 at 2. 4. Minus 3 is way off my graph. And what you might notice is that this first one we draw is going up left to right. So this would be known as like an exponential increase. This would be known as like an exponential decrease or an exponential decay. So sometimes you'll hear this as a sort of exponential decay. Decay as in D-E-C-A-Y, not decay as in Donkey Kong, right? Okay, just thought to clarify. So, what are some characteristics of this? We might notice it's doing the same sort of thing as it's going towards positive infinity, like the other one was going towards minus infinity. So we get this asymptote at y equals 0 or on the x-axis. So here we get a horizontal asymptote. It is decreasing in this first quadrant. So the other one was increasing here. This one decreases. And so they keep referencing the first quadrant. And part of the reason why they keep referencing the first quadrant is because this is where real life happens, right? In positive time. And so if we want to model something that is increasing exponentially, we're going to use this. And if we want to model something that is decreasing exponentially, we're going to use something like this. And we will talk about an example of exponential decrease, I think, in a second. So we could do exponential increases with like populations and bacterias and viruses, things of that nature. Decrease, we're going to have an example and I'll talk about it and what we use exponential decrease for. Okay. Okay, same thing if we plug in a 0 and our C is 1, our y-intercept is going to be 1. It's decreasing in the first quadrant, they call it half-life. It's halving each time. And so I want to jump to this example. They're talking about modeling with half-life. So here they talk about something radon 222 or something is an isotope of radon. I want to talk about something else. So there is this thing that accumulates in living organisms called carbon-14, and it is a radioactive sort of element that accumulates in living organisms. And when they're living, organisms produce this form of carbon. And what's saying it is a radioactive sort of material There are different forms of radioactivity, right? And this is not like this harmful sort of radioactivity, but it does produces this radiative energy, right? It produces radiation, and it's a radiation we can measure, sort of thing. It's an irradiated compound, and so we produce this compound of carbon-14 when we are living, and when we die, we no longer produce it. And what we've noticed is that this thing starts decaying as soon as you die, right? We die and it decays in an exponential fashion. And what we figured out is we can date things and date when they died, right? And this thing is called dating by carbon or carbon dating. And so this is how carbon dating works. We take a carbon molecule or atom. This wouldn't be a molecule. I believe it'd be an atom. So we'd take a carbon atom and look at this carbon-14 and look at how much carbon-14 is present in this organism, and it would tell us when it died. With that said, they got this modeling and half-life. And so I want to start off with maybe something a little more simpler than what they're giving us here. Let's start off with 100 grams of something. And so if I start off with 100 grams, and they might do molecules, what do they do? What percent of the amount? 5 milligrams. Okay, they do stuff in grams. So if we start off in grams, and I tell you every 5 years is the half-life. So what does that mean? After 5 years here, this thing is going to go down to what? 50 grams. After another 5 years, it's going to go down to 25 grams. After another 5 years, it's going to go down to 12.5 grams, right? So if I asked you what happens after 10 years, you could tell me, oh, it's going to be at 25 grams. What happens after 15 years? It's going to be at 12.5. All right, this is all fair and good. What if I gave you something in between and asked you what happens at 12 years, right? Then we might need a formula to sort of figure this thing out. But hopefully this is the pattern you kind of have in your head. And 12 years is going to be somewhere between what, 25 and 12.5. So we should be getting something between 12 and 25, right? Okay, but what are we going to get? So that is where they're sort of getting this formula. If we wanted to know, if we start with 100 grams, and we're going to half it, and we're going to multiply it by half every time we get 5 here. So if we want 12, you might notice 12 divided by 5 is what, 2.4? So we're going to, and like a 0.4 of a half-life through there is what this is also telling me, right? 12 over 5 is like we're going 2 half-lives and a little bit more. We're not going quite 3 half-lives is what this is telling me. So this number up here is giving me sort of the number of half-lives that I'm getting. And the half-life literally means you multiply it by half that many times. And so we're going to multiply it by a half twice and then a little bit more. So 0.5 to the 2.4 is going to give me something crazy, and then multiply it by 100. I'm just going to do this all in one step here. But I should be getting something like 18.95 grams, which is where I expected it to be. But also something you might want to notice, it's probably closer to 25 than you thought it would be. Radon is a naturally occurring radioisotope. Radon-222 is an isotope of radon. With a half-life of 4 days, what percent of the initial amount of radon released remains after 1 week? And if 5 milligrams of radon-222 were released, how much remains after 28 days? So first thing they say is what percentage of the initial amount of radon-222 released remains after 1 week. So there are a few ways to do this. we want to know how much we're starting with. They don't tell us how much we're starting with. What they're actually asking us for is what the factor is here. But if you want to throw in an amount, let's say we start with 100. If we're starting with 100, we're starting with 100%. It will give us something in a percentage then if we start with 100. So if we let A not be 100, it will be a nice round even number to plug into here. So we do A naught is 100, and that's 100 is what I'm starting out with. I'm doing X over K. So the K is the half-life that they gave me, which is 4 days. The X is the amount of time here. So 1 week is giving me my X value, which is the got to be in the same unit that your half-life is in. So 1 week, that's the same thing as saying 7 days. So you have to make sure it's in the same unit as your half-life. But if I start with 100%, I'm going to half it, and I'm going to do 7 quarters. It's going to give me 1 3/4, 1.75. Decimal, it might be easier to plug this into your calculator. So if we do 0.5 to the 1.75, it may be easier to plug in. But what we're saying is 0.2973, I think, will be enough places. And so if I start out with 100 grams or 100 something of this radon 222, I'm going to be left with 29.73 of them. Another way of saying this is 29.73% of the radon is left. What they were really asking for here is the factor. So if you look at just this factor and not the 100 that I plugged in, that's also another way that you can get 29.73%. You just have to convert the decimal to a percentage. Assuming I start out with 100 of the amount, and then I end up with 29.73 of the amount, this will also give me an easy way to get at the percentage. So this is a bit of an odd question because they're asking the factor by which it reduces and not the actual amount by which it reduces, right? And the factor by which it reduces is 29.73%. And I picked 100 because what I'm doing is figuring out how much that is out of that. How much did it reduce by? This is the amount it ended with. This is the amount I started with. So what percentage is this of this? So if I do 100, it's already in a percent. That's a little bit of picking your numbers smarter, so you have to do a little bit less work in the end, right? But basically what they're asking for is the factor. This one I think is a little more straightforward with using the formula. If 5 milligrams of radon are released, how much remains after 28 days? So this one, we are trying to find A of X. They're giving us our A naught, or the starting amount is the 5 milligrams of radon that we're starting with. And so this is like my A naught. And so I might have skimmed over it a bit, but this is the final amount that you're going to be left with. This is your starting amount, or A naught, or A at 0. And this is like my X is my variable and my K is my half-life. If 5 milligrams of around 222 are released, how much remains after 28 days? So my A naught is the 5 that I'm starting with. The 1/2 is there. My K is still the same. It's still 4. My X is the thing that is 28. This is 5 to the 1/2 looks like 0.5. 28 divided by 4 is going to give me 7. So what I'm doing is I'm having the 7 times. You're doing 0.5 to the 7 and multiplying that by 5. So this is going to give me 0.0078125. And then this is going to give me 0.0390625. 0.0390625. If you round this to what? Probably 3 good numbers in that decimal. 3 significant figures, probably something like that. 391. That would probably be close enough. And we're talking about here, this thing has units of milligrams. Okay, so we start with 5 milligrams. After 28 days, we're going to be left with a really small fractional amount of a milligram. All right, so that is the final problem, and I will see y'all soon. Take care.